All right, in this final section, what I want to do is talk about how to statistically describe fading. So as motivation for that, fading, of course, depends on the particular multipath distributions, and specifically the gains and the angles of arrivals of the different paths. But of course, multipath in general will be site-specific. So for example, shown here are some ray tracing outputs, and the actual paths that would arrive depend on the particular locations of the walls or the buildings of that environment. What we want, though, to discuss in this section is a statistical model. So this is a model that is not site-specific, but instead describes a probability distribution of channels that would be trained on an ensemble of some ensemble of channels from some environment. Now, the reason we want to do that is usually for the evaluation of communication systems. So, for example, I might want to question how well does a system do on average? So in contrast, I could say, well, if it was this particular building, I placed a transmitter here and I placed a receiver here, and the person was walking along this corridor, I would get this particular fading path. And then I could say, well, in that particular circumstance, the receiver will work well or not. But what if I want to ask a question, well, how well does it do on average amongst typical buildings or in typical areas, or what kinds of probability I get of coverage? For these kind of questions, I need to have a statistical model. So let's start with the very first simple statistical model for paths. And what we try to do in these statistical models is try to model the path parameters as random variables. Now, the simplest model is that we say that there are a number of paths, and each path can be described by a set of gain, delay, and angles of arrival. And we'll then say that in one very simple model is that the time varying frequency response we know was given by this equation, but we'll say that the number of paths are very large and all of these path coefficients are independent. And just to make this simple, let's say that the path gains have zero mean and they all have a common variance, which I'll denote by G0. Now, the zero mean could happen just, for example, if the phase of that coefficient is random, and if the phase of the coefficient is random and uniformly distributed, it will have a zero mean. All right, in this case, if you have a large number of paths, that time-varying frequency response will end up looking like a complex Gaussian. And that's just a simple consequence of the central limit theorem, because I took zero mean variables with this scaling coefficient. Once it becomes a complex Gaussian, because I'm adding on these large numbers of paths, what that means is that the real and the imaginary components will be independent, and each of these will have a power of in each dimension by G0 divided by 2. So what we saw from the previous slide is that when you have a large number of paths, and each path has independent parameters, and all the paths are roughly equal, the resulting time or frequency response at a particular time and frequency will look like a complex Gaussian with some average power G0. This type of statistical distribution is called a Rayleigh fading, and the reason is following. So let's let R be the magnitude of this channel response. So that represents the amplitude gain, if you like, of the channel. In that case, that R, which will be a random variable, because H is a random variable, will have a very well-known distribution called the Rayleigh distribution. And that distribution is shown here. The Rayleigh distribution is parametrized by this average power G0, and you can get its PDF or CDF from many sites like the Wikipedia here. Although it's called the Rayleigh distribution, it's actually easier to look at what the related distribution called the exponential distribution. And again, suppose we have a Rayleigh fading channel, which is complex Gaussian, and we know its magnitude is Rayleigh. So that means it has this CDF or complementary CDF given by this. But then if we look at the instantaneous gain of the channel, which is the magnitude squared, turns out that this will have always an exponential distribution. As I can show this distribution here, the complementary CDF. So that means that the probability that it's large decays off exponentially, and it will be parametrized by the mean, which in this case is the mean power gain of the channel. All right, let's use this to do a simple calculation. Suppose I have a channel and it experiences Rayleigh fading, and I want to compute the probability that the channel is 15 dB below the average. So that's called a 15 dB fade. Now that's actually pretty significant. That means that if you were at 20 dB on average, that means a 15 dB would push you all the way down to 5 dB. And that will have a number of consequences that we'll talk about in the next unit. All right, how do we compute this? Well, this is a really easy math calculation. So the gain being 15 dB below average means that the gain is less than this constant times the average gain, G0. All right, and that's this scaling here by 15 dB. But we know from the exponential distribution that the probability that the gain is below some beta times G0 is just simply given by this formula. The G0s cancel out, and you get this expression. So as a function of the amount of the fade, which is beta. So I graph that here. So here's the fade. So for example, the probability that's the fade is 10 dB is a certain value, about 0.1. Probability is 20 dB is 0.02, and so on. All right, for small beta, you just do a simple simplification of this using that e to the minus beta. It's approximately 1 minus beta. So you get that probability is beta. So the probability that it would be, say, 20 dB, which would be 0.01 in linear scale, that probably about be 0.1, which is, as you can see here, 0.01, which you can see here. In our case, we're interested in a 15 dB fade. So a 15 dB fade is here, and that probability is about 0.032, or about 3.2% of the time. Now that might not seem very likely, but just imagine that you're trying to build a reliable system. Even 3% of the time getting that error could be significant. Okay, so as before, we have our time-varying frequency response. It's given by the sum of a large number of paths, and we're trying to model these paths as IID when L is large. So what we saw up to now is that if you fix the time and frequency, that complex gain is a complex Gaussian because it is a sum of a large number of IID components, and we applied the central limit theorem. But what's also interesting is that as the time or the frequency varies, that process can be considered as a Gaussian random process. Gaussian random process is just any variations in time or in frequency which are jointly Gaussian. Now, whenever you have a Gaussian random process, you can describe what is called its autocorrelation, which is the expectation, the correlation between one time and frequency and another time and frequency separated by delta t and delta f. In this case, this autocorrelation function can be directly computed from this expression here, and this will tell you how correlated this process is over time and frequency. Now, this particular expectation will depend on the distributions of the angles and the distribution of the delays. And we're going to walk you through some examples to see how that works out. So with that in mind, let me talk about a very important type of distribution called the Jakes model. So for this, let's just fix a frequency. So this is, you could consider this a narrowband response. And then that time-varying frequency response simplifies because I can just take the terms for that frequency and absorb them into the gain. In this case, the only variations are over the angles cos theta L. So when we look at the correlation of this process, it will just depend on this angular distribution. So there are different models for the way that the angles are distributed, but one simple model is called the Jakes model. There's some different variants of this. So one model is just to assume that the angles are uniformly distributed from 0 to pi. That means I have paths coming in from every possible angle uniformly. So it's an extremely rich, scattered environment. So if you were to simulate one realization of that process, it will change over frequency here, and the rate of that change will depend on this maximum Doppler shift. So this is this kind of typical one realization of this, of the gain. Remember, it's a complex process, so its phase is also varying. There are also what you call asymmetric Jakes processes. In this case, the angles are not from 0 to 2 pi, but from between two angles. So something representing, say, a path that has maybe a diffuse scattering. When you have a restricted angle, it's still a complex Gaussian process, but it will actually vary at a much slower rate, as you saw two different examples of the asymmetric jakes here. Now, those plots that I showed you in the previous slide, you can actually generate, you can easily generate it manually, writing some code to do this, but Matlab has some excellent tools for generating fading of models, so you can check these out in the demo. Just to show you a little clip from that. What I've done is I created different Doppler models that I wanted to simulate, and you just call this Rayleigh channel object, you give it the sample rate, the maximum Doppler, and so on, and it will actually then easily, you can pass a signal through it, and it will give you the gain and the resulting faded output. All right, let's go and look a little bit more at this autocorrelation function, which I mentioned. So what I said here, if you look at the Jakes model, I said for a fixed frequency, this autocorrelation over time is given by this expectation. And it depends on a few things. Depends on the time difference of points that I'm looking at. It depends on the maximum Doppler. And it depends on the angle distribution of this theta L. All right, so what I've tried to do here is plot this autocorrelation for a couple of different models for the distribution. So specifically, I considered the angles distributed uniformly between some minus theta m and theta m, right? And in this blue line, I plotted it where it's uniform between minus 180 to 80. So in other words, basically the full classic Jakes model. And then I also looked at narrow angles. So what you can see here is that the rate of decorrelation is very large. In particular, this is plotted in what you call the normalized frequency here, which is the time delay multiplied by the maximum Doppler. And once it's at about half or maybe about 0.4 of away from the that normalized frequency, basically the two paths become uncorrelated. And since they're Gaussian, they basically are independent. Now, what does that mean? So this value will be about 1/2, when that time delay is about 1/2 times the maximum Doppler shift. And that, if you recall, is what I was calling before the coherence time. And now we have a statistical way to think about coherence time in the following sense. That when you're split up at about one of the coherence time, the two times or the two complex gains become independent. So what you know about the channel at time t0 will be independent to what you know about the channel at about t0 plus or coherence time. On the other hand, when the angular distribution is much smaller, you'll see that the coherence time is much larger because it takes a much longer time for the channel to decorrelate. In other words, that means that the process will vary much more or slowly over time. And this is very important when we're also thinking later about millimeter wave systems, which have highly directional antennas. Since they receive the signal in only a very small, narrow directional directional angular space, the process will vary much slower in that sense. And that will have lots of implications when we think about channel tracking, as we'll talk about later on in the class. All right. Just on the last plot, again, what I did is I computed those numerically, and I'll show you how to do that quickly in Matlab. So what we wanted to do was compute this autocorrelation, which is this expectation, which means I would want to compute the integral of this with respect to the probability distribution. In general, there's no closed form expression for this, so you want to do what's called numerical integration, basically do some kind of approximation of this as a sum. So you can write your own numerical integration routine, but Matlab has really excellent tools to do this, so you don't have to. Basically, for example, you just give it the integrand, all right, and then you give it, I tested in this over some different uniform intervals, and then you can call this integral function here, all right, which will then actually perform that integral on some boundary, right? And you can look at this code and then create this plot. So this is another very powerful tool in Matlab that you can use if you need to compute these kinds of integrals. All right, so I talked before about coherence time and coherence frequency. Let me revisit these concepts in the context of a statistical model. So imagine we have a time varying frequency response, ht of f. the coherence time is roughly the duration of time that can transpire where the channel doesn't change significantly. So that means mathematically that if you're at some time in frequency and you shift the time delta of t within the coherence time, the channel should be roughly the same. And this is roughly related to what we saw before, the Doppler spread, meaning the 1 over the difference between the maximum Doppler shift and the minimum Doppler shift. And we saw that specifically in this statistical model. Similarly, we can also think about the coherence bandwidth, which is the maximum change in frequency over which the channel would be constant. And this turns out to be related to the inverse of the delay spread, meaning the maximum difference between the time delay of the latest path and the earliest path. All right, and what we'll see is that both the coherence time and coherence frequency will have a lot of implications for many other procedures. You could imagine for tracking the channel in time or frequency, for the way we code and when we do auto repeat request, and we'll talk a lot about this throughout this class. All right, what we had up to now was just a model at a particular frequency. But if we want to get a wideband model, which means we need to model the channel over multiple different frequencies, we need to extend what we did. Now, when you look at a particular frequency, we saw that the variations in time only depend on the angular distribution. But what you would need for a wideband model is also to have a distribution of the delays. So one classical model for this is called this Winner 3GPP model, and it's based on a fairly reasonable geometric view of the channel. So what you do is you describe the paths as having some arriving in various clusters, and each cluster physically corresponds to some sort of macro level path with some scattering. Now within the path there are what are called subpaths, and these paths will have very close delays, but they will have some angular distribution dependent on the level of diffusion of the path, the amount of diffuse scattering in that path. And then there's a random, typically, number of paths, and each will be given a random number of parameters. I won't go through in this lecture all the details of this model, but you can check it out and easily play around with this. There are a lot of tools for simulating these types of paths. Maybe I'll have you simulate one of these in one of your labs. All right. A couple things I just want to wrap up the discussion with is that we saw many mechanisms for the way path loss can vary. So for example, path loss can vary just simply because you're getting further from the transmitter. That you could call it distance-based path loss. It can also vary because of shadowing. Those are blockages in the path. But it can also vary from what you would call small-scale fading, which is what we saw here. And this would just vary even by very small levels of degrees of motion because of the constructive and destructive interference of various paths. Now the important part here is that these occur at different time scales. So this will occur, the distance-based path loss will occur very slowly, while the small-scale multipath fading occurs much faster. So this is a picture from Andrea Goldsmith's book to illustrate this. So you're traveling at some distance. You will see the distance-based path loss kind of goes very slowly. There would be maybe some variation of the shadowing around this because maybe you're going between buildings and so on. But within the level of maybe about 0.4 or half of a wavelength, you can actually get even faster rates of fading due to this multipath small-scale fading. So we can kind of summarize that, if you like, in this table which I've tried to put here. So here's our three mechanisms for variation: the small-scale fading, what you could call the large-scale fading due to shadowing, and then the path loss variations. And for each one of these, we have some kind of mathematical model, like the Rayleigh distribution, or we might have a log normal distribution for the large-scale fading, or a path loss exponent. And each of these occur at much different either spatial coherence or temporal coherence, depending if you have a motion. Some being maybe in the orders of meters or even less than meters, and some being in the orders of tens or even hundreds of meters. So when you're thinking about simulations, you want to think about what time scale you're doing the simulation on to try to pick the appropriate model. All right, that wraps up everything I want to say in this unit. So you can go ahead and do the lab of this and then go on to the next unit.